Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear so that we can start with the session. So all the candidates who are live with me, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear. Till you are going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. So the ideal duration for this session is going to be approximately one and a half to 2 hours. And the agenda for today's session is that we are going to discuss complete load flow analysis. Load flow analysis is one of the important topic in power system from where questions are expected. So we'll be going through all the concepts, but at the same time the important concepts from where there is a high possibility to get a question, we are going to focus more and more. So let us start with the session. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11+ years of teaching experience. MTech from BYJU in 2010, written a couple of books, and these are my areas of expertise. Before we start the session, a very important information about the BYJU'S Exam Prep Mega Mock Challenge, which is All India Open Mega Mock Test for GATE 2023. The idea is to strive towards the success in GATE examination. It is going to be conducted from 24th of January to 30th of January, but you have to register yourself to attend these Mega Mock Tests, and it is going to be quite important for your real examination. Everybody's favorite and a great faculty, Joshit Sir, is going to take a workshop on 5 factors to guarantee all India rank under 100 in the GATE 2024 examination. This workshop is going to be conducted on 24th of January, that is tomorrow, 7:30 p.m. in the evening. To attend this workshop, you have to get yourself registered in the BYJU'S Exam Prep app. Now, one of the most awaited session for all the aspirants, all the GATE and engineering services aspirant, is the live GATE analysis that BYJU'S Exam Prep is going to conduct for GATE 2023, electrical, electronics, instrumentation and computer science. It is going to be conducted 5th of February to 11th of February, 1 p.m. and 6 p.m. So to attend these live analysis, you have to subscribe to the BYJU'S Exam Prep if you have not subscribed, so that you do not miss these important sessions. So hi everyone, once again welcome to the session. Again, 2 legendary faculties, Rakesh Talreja sir and Ankit Joshi sir, they are going to conduct the non-stop maths marathon session so that you can score 13 marks in 2 days. The sessions are conducted on the app, BYJU'S Exam Prep app, on 21st and 22nd of January. You can attend these sessions. Now, like the session, hit the bell icon and subscribe to BYJU'S Exam Prep if you have not subscribed, so that you do not miss any of the important session. Let us start with the load flow analysis. If we talk about the load flow analysis, the first thing that comes to our mind is the network matrices, because without understanding the Ybus, if you don't have a command over Ybus, you will not understand how you are going to perform the load flow analysis. So the first topic that I'm going to discuss is network matrices. When I talk about network matrices, basically we have 2 choices. The first one is admittance matrix, which is popularly known as Ybus, and we have the impedance matrix, which is popularly known as Zbus. Previously, Zbus was used for the load flow analysis, but now yes, Rohit, we'll be planning. Don't worry. We'll be planning those sessions also. Okay. So the important part of load flow analysis is admittance matrix and the Zbus matrix, that is the impedance matrix. Previously, the Zbus was also used for the load flow analysis, but there are certain advantages in Ybus matrix. That is the reason why now Ybus is used for the load flow analysis and the stability analysis, whereas Zbus is majorly used for fault analysis only. I hope it is clear. Okay. So that is what I am saying, that Zbus was initially used, but now Ybus is used because it has certain advantages, like it is a highly sparse matrix. Ybus is a highly sparse matrix. What is the meaning of highly sparse matrix? Highly sparse matrix means most of the off diagonal elements are going to be 0. Majority of the off diagonal elements are 0, because you know that diagonal elements cannot be 0. Diagonal elements of Ybus cannot be 0. Why? We will understand. Why? We will understand. Also, it is a symmetrical matrix. Symmetrical matrix means what? Let me write it again. It means Yij is equal to Yji. We'll understand this property also. So if you talk about the Ybus formulation, if you want to understand how the Ybus is formulated, there are basically two methods. The first method is direct inspection method. In this method, you can directly observe the network, you can draw the required circuit or diagram, and you can write the Ybus. In the second method, you have to use the matrices, that is the incidence matrix, okay, and primitive admittance matrix or primitive impedance matrix to find the Ybus matrix. This method is known as singular transformation method. First, we will talk about the direct inspection method, and then we will talk about the singular transformation method. What are the cases when you are going to use the singular transformation method? Basically, if it is a very complex network, then it is always suggested you go with the singular transformation, because computers are going to do the analysis, not individually you are going to do manually. Then if the mutual coupling is present between the lines, mutual coupling between transmission lines is present, then you have no other choice but to go for the singular transformation method, because you cannot find the Ybus by direct inspection method in that case. So everybody just tell me in the comment section, are you able to follow up to this much or not? First, we are talking about the network matrices, that is Ybus and Zbus. This is one of the important area from where you may get a question this year. Okay, so we have to follow it. If you talk about the direct inspection method, suppose there is a circuit, there are two generators G1 and G2. Suppose it is not G2, it is G3. Now at the second node, there is no generator connected. Node 1, 2, 3, there are 3 nodes. This 0 is the reference node. And you have connected generator G1 and G3 like this. The line between 1 and 2 is Y12. The line between 2 and 3 is Y23. Y10, Y20 and Y30, these are the shunt elements or shunt admittances connected to the various buses. Now the first step to write the Ybus is you have to replace all the voltage sources by their equivalent current sources, because we want to separate the impedance or the admittance part from the voltage source, and that is the reason you are going to draw the circuit something like this. The voltage sources you have replaced with the equivalent current sources. Admittance is going to come in the shunt. This is going to be Y10, okay, this is Y12, Y23, Y20 and Y30. Perfect. I1 and I2. Now Ybus is used for the stability analysis and the load flow analysis, already discussed. And if there are n buses in the system, then the order of the Ybus is going to be n cross n. What is the meaning of n cross n? It means there are n rows and there are n columns. So what is the total number of elements in the Ybus? Total number of elements are going to be, including 0 and non-zero elements, it is going to be simply n square, if n is the number of buses in the system. Is it clear, everybody? Perfect. So we are defining our Ybus for a 3 cross 3 matrix. If there are 3 buses in the system, it is going to be a 3 cross 3 matrix. So it is going to be Y11, it is going to be Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32, Y33. So we can divide this matrix into 3 parts. This is going to be the diagonal elements. This is how we are defining the diagonal elements. Diagonal elements are y11, y22, y33. Now if you see, this is what we are defining as upper triangular elements. Upper triangular elements. And this one we are defining as lower triangular elements. Lower triangular elements. I hope it is clear. So what was the first step? Replace all the voltage sources by their equivalent current sources, and all the branch impedances must be represented in the admittance form, because you are writing the Ybus. So all the branches, all the elements, all the shunt elements, it must be in the admittance form. This is one of the major mistakes committed by various students in the pressure of examination. If he is asking to form the Ybus, don't get hasty and don't get worried about the time, and take your time and solve it properly. First change all the, if it is given in impedance, you have to change it into the admittance. So finally you are getting this type of network. You have 3 buses, 1, 2, 3. How you are writing the diagonal elements, that is YII. YII is the diagonal element. It is defined as the sum of all the branch admittances, not impedances. Sum of all branch admittances directly connected to the ith bus. It means if I have to write Y11, can you tell me what are the direct elements, admittances connected to it? Y10 plus Y12. So it is Y10 plus Y12. What is Y22? What are the branch admittances directly connected to it? Y12, Y23, Y20. Y12, Y23 plus Y20. What is Y33? Y23 plus Y30. Y23 plus Y30. Is it clear for everybody? Just tell me yes or no. Now if you want to write the off diagonal elements, they may be upper triangular or lower triangular. But the beauty of this Ybus matrix is that it is a symmetrical matrix. So if you write Y12, then Y21 is going to be same. So if you are writing YIK, it is minus of small yik. So if there are 2 nodes, suppose like this, this is ith node, this is kth node, and in between these 2 nodes there is one element whose admittance is yik. So what is going to be yik? It is going to be minus of small yik. Minus of small yik. And it is going to be same whether you find yik or yki. Simply you can write like this. I hope it is clear for everybody. If the ith and kth node, they are not directly connected, then the off diagonal element yik is going to be 0 if node I and k not connected directly. If they are connected directly write minus of negative sign and admittance connected between the ith and kth node. I hope it is clear. So if you follow this, can you write Y12? Yes. Y12 will be same as Y21 and it is minus Y12. Can you write Y13 or Y31? Same thing. Because 1 and 3 are not directly connected, so this off diagonal element is going to be 0. What is Y23 or Y32? 2 and 3 directly connected? Yes. What is the branch admittance between them? Small y23. So it becomes minus of small y23. I hope it is clear. So you have all the elements now. Can you write the Ybus? Can you write the Ybus now? Yes. So I'm finally writing the Ybus for you. Okay. I'm writing it here. I hope you can follow it. So your Ybus is going to be, it is Y10 plus Y12. What is Y12? It is minus Y12. Y13, 0. What is Y21? Minus Y12. Y22, it is Y20. Y12 plus Y23. And Y23 is minus Y23. Y31, 0. Y32 is minus Y23. And Y33 is Y30 plus Y23. So this is going to be your Ybus matrix. It is a 3 cross 3 matrix you have just found. Is it clear, everybody? I hope it is 100% clear, no doubt. Now there is one characteristic of this Ybus matrix, and that characteristic is if you add all the elements of a particular row, because this row belongs to node number 1, this row belongs to node number 3, this belongs to node number 3. So if you add all the elements of a particular row related to a particular bus, then it is going to give you the shunt element connected to that particular node, because Y10 plus Y12 minus Y12. So what you are getting? If you add this, simply Y10. If you add all the elements of the second row, minus Y12 and minus Y23 will be cancelled, and you will be having Y20, which is nothing but the shunt element connected to the second bus. If you add all the elements of the third bus, minus Y23 plus Y23 cancelled, Y30. What is Y30? Is the shunt element, shunt admittance connected to the third bus. This is the important characteristic. You can get a question, you may get a question on this characteristic. Yes. Now let us talk about the sparsity of the Ybus matrix. What do we mean by the sparsity of the Ybus matrix? I told you the main advantage of Ybus matrix is that it is a sparse matrix. Sparse matrix means majority of the off diagonal elements are going to be 0. Why off diagonal? Why cannot diagonal? Because diagonal element can never be 0. Why diagonal element can never be 0? How you are defining the diagonal element? You are defining the diagonal element as sum of all the branch admittances directly connected to the ith bus. If it is 0, I will change it, Ram, please wait. If the diagonal element is 0, it means it is an isolated node. It is not the part of your network. Yes or no? Yes. That is the only case when the diagonal element can be 0. But if this is the case, don't say sorry, don't say sorry. Okay, it's not about to say sorry. Let me come to that point, then I will correct it. So I hope you understand that diagonal element can never be 0 in a Ybus, and it should be 100%. Common sense. So sparsity of the Ybus matrix says that majority of the off diagonal elements of the Ybus are going to be 0. So there is a less memory requirement for the analysis of load flow. Now how we are defining the sparsity? It is the ratio of number of 0 elements divided by total number of elements multiplied by 100. Now because of the sparsity and the symmetric nature of Ybus matrix, the memory requirement is quite less, comparatively quite less. I hope it is clear. Let us do a question on this sparsity of Ybus matrix. It is saying a power system network contains 50 buses in total. The number of transmission line is 120. So number of transmission line is 120. Number of buses is 50. He is asking find the sparsity of the Ybus matrix. So in order to find the sparsity of the Ybus matrix, you want to know number of 0 elements. Now 0 elements are going to be high in number because Ybus matrix advantage is that majority of the off diagonal elements are 0. So it is better to find the number of non-zero elements because they are less. So the number of 0 elements is going to be total elements minus number of non-zero elements. It is going to be better. Now how to find the number of non-zero elements? Please understand. Number of non-zero elements is going to be number of diagonal elements, because diagonal elements cannot be 0, plus number of non-zero of diagonal elements. Yes or no? Now you tell me one thing. If there are two nodes I and K, and in between them there is some admittance connected YIK, then how many elements you will be getting for one transmission line? This is one transmission line. This one transmission line gives you two elements. It gives you YIK and YKI. It means one transmission line gives you two elements in the Ybus. So if there are 120 transmission lines, how many non-zero off diagonal elements you will be getting? See here. Number of non-zero elements. Number of diagonal elements 50 bus. So number of diagonal elements 50. Number of non-zero of diagonal elements, it is 2 times the number of transmission lines, that is 120. So it is how much? 240 plus 50, 290. What is the total number of elements? Total number of elements will be 50 into 50, that is 2500. Can anybody find the sparsity of the Ybus matrix? Let me add one page here. Sorry. So my friend, you got the total number of non-zero elements, yes or no? You got the total number of non-zero elements, diagonal elements, and 2 times the number of transmission lines, that is 290. What is the number of zero elements? Number of zero elements will be total elements 2500 minus non-zero elements, that is 290. So what is the sparsity? The sparsity of the Ybus matrix is going to be 2500 minus 290 divided by 2500 multiplied by 100, that is percentage. Is it clear, everybody? Just find what is the answer. So I'm not sure, somewhere around 88 point something you must be getting, just calculate it, 88.4, perfect. So everybody understood the point, that number of transmission lines given, so you can easily find the number of non-zero off diagonal elements, because one transmission line gives you two non-zero off diagonal elements. So if you know the number of transmission lines, very easily you can find the number of non-zero off diagonal elements. Let us do this question. The Ybus is given, he is asking find the shunt elements and their nature. So node number 1, just add all the elements, minus J20 plus J10 plus J5. So it is, what you are getting is, sum is minus J5. Bus number 2, 0.5 minus 0.5 cancelled, minus J30 plus 10 plus 20, so it is 0. Bus number 3, just add all the elements, 0.5 0.5 cancel, 5 3 8 minus 10 minus J2. Bus number 4, J20 cancelled, simply J3. Now listen very carefully. What you have written in this Ybus matrix. Yes, Ram, listen. These are the admittances. If you are getting admittance negative, Listen very carefully. If you are getting admittance negative, it means it is inductive in nature. Hello? Are you able to follow this? Admittance, if you are getting negative, the imaginary part, it means it is inductive in nature. Because when you write it for the reactance, suppose reactance value, impedance, imaginary value, you are getting negative, it means it is capacitive in nature. Are you getting this? Second bus, 0. No shunt element connected. No shunt element connected. Minus J2, again inductive in nature. Plus J3, capacitive in nature. I hope it is clear for everybody. Let us talk about the singular transformation method. Singular transformation method is used when the system size is too large, number of buses are very large. When mutual coupling is present between the transmission lines, then also you have no other choice but to go with the singular transformation method. It's okay, Ram, don't worry. How you are finding the Y bus? It is simply A transpose Y prime A. Now what is A? A is the reduced bus incidence matrix. We'll understand what is this reduced bus incidence matrix. Then what is this A transpose? A transpose is the transpose of the reduced bus incidence matrix. Y prime, what is Y prime? It is the primitive admittance matrix. It is a branch cross branch matrix. We'll understand how to make it. Everybody just focus here. First, we'll understand how to make the complete incidence matrix. If you know how to write the complete incidence matrix, just remove the column which is related to the reference bus, 0 bus, and you will be getting the reduced incidence matrix. For example, suppose there is a graph. Okay, this graph has, please understand the graph first, then I will tell you how to make the incidence matrix, complete bus incidence matrix. This is the reference node. Okay, 0. This is node number 1, this is node number 2, this is node number 3. Now there are 6 branches, 1, 2, 3, 4, 5, and this is 6. This is simply 6. Okay. The orientations are also mentioned, 1 to 0, 2 to 0, 3 to 0, 1 to 2, 2 to 3, and 2 to 3 again for 6. So this is your graph given. I hope you are able to follow this. Everybody is okay with the graph? You understood? Now your complete bus incidence matrix is a branch to node matrix. Branch to node matrix means what? We understand. Suppose, let me add one page here so that you can understand it better. So everybody just confirm that graph is clear for everyone so that we can proceed. Okay. So how many branches are there? How many branches are there? Number of branches in this graph is given as 6, and number of nodes in this graph, there are 4 nodes including the reference node also. So what is the logic we are using if we are writing the complete bus incidence matrix? Any particular element we are writing as 1. Suppose AIK we are writing as 1 when the ith node, it is not branch, ith node connected to the kth node and the orientation is away from it. Orientation is away from it. Any element is going to be -1 when the ith node is connected to the kth node and the orientation is towards it. Let me give you a simple idea what we are doing. Suppose this is ith node and suppose this is kth node. If the ith node is not directly related with the kth node, it is going to be 0. If there is no transmission lines, then it is 0. If there is a transmission line, suppose it is connected like this, and the orientation is like this. Listen very carefully how I am writing. I am writing not yik, because it is incidence matrix. So I will be writing AIK. Listen very carefully. I and K, it is present. Yes, ith node and kth node, it is present. When it is away from I, then it is going to be +1. So if you are writing IKI, suppose I am giving you just one idea, then it is going to be what? Towards, or let me just do it. Okay. Let me do it, otherwise you will be confused. This is branch number 1, 2, 3, 4, 5, 6. Node number 1, node number 2, node number 3, and node number 0. Let me do it here so that you get a better picture, otherwise you will be confused. Okay. How I am going to do is, first you hold a branch. Suppose branch number 1 you are holding. The branch number 1 is between which and which node? Branch number 1 is between which and which node? Branch number 1 is 1 and 0. It is away from 1 and towards 0. So towards 0 is, so 0 is -1 and 1 is plus because it is away. So you can write branch number 1, it is +1, it is -1, rest 0. I hope you are getting this. Everybody just tell me yes or no. Branch number 1 connected between 1 and 2, away from 1, so +1, towards 0, so -1. Branch number 2. Branch number 2 is between 2 and 0, away from 2, so 2 will get +1 and 0 -1. So 2 and 0, 2 and 0, and it is rest are 0. Branch number 3. Branch number 3 is between 3 and 0. 3 away from 3 and towards 0, rest are 0. Branch number 4. Branch number 4 is between 1 and 2, away from 1 towards 2. So 1 and 2, 1 positive, 2 negative, rest 0. Branch number 5. Branch number 5 is between 2 and 3, away from 2 towards 3. So 2 positive, 3 negative. 2 positive, 3 negative, rest 0. Branch number 6. Branch number 6 is again between 2 and 3, away from 2 and towards 3. So 2 positive, 3 negative. 2 positive, 3 negative, rest 0. So this is going to be 6 cross 4 complete bus incidence matrix. This is a complete bus incidence matrix. I hope it is clear for everybody. Everybody can write this? No. Now if you want the reduced bus incidence matrix, then you just remove the column related to the reference bus. Just remove it, and whatever you are getting 6 cross 3 matrix, that is your reduced incidence matrix. Now the second thing is how you are writing the primitive admittance matrix. Primitive admittance matrix is a branch cross branch matrix. It is a Y prime. It is a branch cross branch matrix. So it is 6 cross 6 because there are 6 branches. All the branch admittances you are going to write in the diagonal. Y1, Y2, Y3, Y4, Y5, Y6, and rest all the elements are 0. Rest all the elements are 0. This is your Y prime. Y prime or primitive admittance matrix is a diagonal matrix where each diagonal element represents the branch admittance. Okay. So you can write this also. So if you have the reduced incidence matrix A, and if you have the primitive admittance matrix, very easily you can write Ybus. It is going to be A transpose. This is going to be A transpose Y primitive, and this is A. Just put the matrices and you will get the Ybus. I hope it is clear. Let us take the most complex case. If the mutual coupling is present between the lines, If the mutual coupling is present between the line, then there is a little change in the procedure. The change in the procedure is, the first step is you have to find the Z prime primitive impedance matrix first, and then you have to take the inverse of that to find the Y primitive, that is inverse of Z. And then you can put it in this equation and you can get the Ybus. How you are writing the Z prime when mutual coupling is present, this is important. Suppose I am saying that mutual coupling is present. Suppose I am saying mutual coupling is present between 1 and 2 and 5 and 6. These are the branches. 1, 2, 5, 6 are the branches. So the element in the impedance, primitive impedance matrix, diagonal elements, you will be putting the impedances, branch impedances, Z1, Z2, Z3, Z4, Z5, Z6. But the branches in between which you have the mutual coupling, for example, between 1 and 2 you have the mutual coupling. So there will be two elements coming in the Z bus. Sorry, not Z bus, primitive impedance matrix, that is Z12 and Z21. I hope you are getting this. This is Z12 and Z21. Similarly, if the mutual coupling is present between 5 and 6, then again you will be getting two elements, Z56 and Z65. Apart from this, whatever elements are there, they are going to be 0. This is how you are writing the Z prime. This is how you are writing the primitive impedance matrix. Once you get it, just take the inverse, you will get Y prime. Is it clear, everybody? So let us do one problem so that you understand the procedure well. This year there is a high possibility that you will get a question on this. So everybody will do with me. Are you ready for that? Modification I am removing because this you can do because we have much more to discuss. Just one question I am going to do here, which is more important. Okay. So this is your network given. There are 3 buses, 1, 2 and 3. Because the reference bus is not given, so whatever incidence matrix you are going to write for this given network, it is going to be the reduced incidence matrix directly. How many branches are there? How many branches are there? Suppose this is 1. Suppose this is 1, this is 2 and this is 3. Okay. The impedances are Z1, Z2, Z3. In between 1 and 3, branch 1 and 3, it is Z13. In between 2 and 3, it is Z23, mutual coupling present. So the first thing I'm going to do is I'm going to write the reduced incidence matrix. Reduced incidence matrix, there are how many branches? 3 branches. So 1, 2, 3. How many nodes are there? 1, 2, 3. Branch number 1. Branch number 1 is between 1 and 2, away from 1 towards 2. So 1 positive, 2 negative, rest 0. 1 positive, 2 negative, rest 0. Branch number 2. Branch number 2 is between 1 and 2 again. 1 positive, 2 negative. 1 positive, 2 negative, rest 0. Branch number 3. Branch number 3 is between 3 to 2 and the orientation is away from 3. So 3 positive, 2 negative. 3 positive, 2 negative, rest 0. So this is going to be your reduced incidence matrix. Very easily you can find. Directly you can find reduced incidence matrix. Now because mutual coupling is present, so primitive admittance matrix directly you cannot find. So first you have to find the Z primitive. How you are going to find it? It is a 3 cross 3 matrix. The diagonal elements are going to be Z1, Z2 and Z3. Yes or no? Mutual coupling is present between 1 and 3. So you will be getting one element here, Z13, Z31, or simply if you want you can write Z13 here also, same thing because it is same. Again, mutual coupling is present between Z2 and Z3. So it is going to be Z23, and here also you will be getting Z23, and rest elements are going to be 0. This is your primitive impedance matrix. Can you find the Ybus? Sorry, can you find the primitive admittance matrix now? Can you find Y prime? Yes. It is going to be the inverse of Z prime. It is going to be the inverse of Z prime. I hope it is clear for everybody. I'm not going to the exact calculation because that will take much time. Okay, and we have to do a lot of things today. So I hope now you can do it. Yes, everybody. Now let us talk about the Z bus, because we are talking about Y bus, so it is important that we talk about Z bus also. Generally, they are not going to ask you direct questions on Z bus because it takes a lot of time to formulate the Z bus, because it is a brick by brick method. You assume that initially there is nothing, and then you bring first one element, one node, another element, like this. Step by step, brick by brick, you have to build the Z bus. There is one more method. If they are asking a question on Z bus, one smart thing what you can do is, instead of following this Z bus building algorithm, directly you can write, sir, Z bus is inverse of Y bus. Y bus you can easily find by using the direct inspection method in the examination. Just take the inverse and write the Z bus. Who is checking whether you are following this method or this method? I hope it is clear for everybody. Yes, everybody. Okay. Now, as I am saying that Z-bus building algorithm is a brick by brick method. Brick by brick method means one by one you have to add the elements, the new node in the system, and then the whole network is going to be built. So there are basically 4 possibilities in which you can add a new element to a system. For example, type 1. Type 1 modification. It is defined as when a new element is connected between a new incoming node and the reference bus. Already there are n buses. This is 1, 2, 3 up to n. Now the new node which is coming is Q, and the new element is ZS, and it is connected between the new incoming node and the reference bus. So number of nodes are becoming from n to n plus 1. It means the size of the Y bus is going to, size of the Z bus is going to be increasing by 1. Yes or no? So how you are writing? Just write the old Z bus here, write the old Z bus here, add a new column and a new row. All the elements are 0 except the diagonal element. The diagonal element you are going to write the new element which you are going to connect between the new incoming node and the reference bus, that is ZS. And what is the size of this Z bus? It is n plus 1 into n plus 1. Is it clear, everybody? Write the old bus, add a new column and a new row. The diagonal element is ZS, and rest all the elements of the new added column and row is 0. This is how you are going to write the type 1 modification. Type 2 modification. When a new element is added between the new incoming node and the existing bus, it is not the reference bus, not the reference bus, not the reference bus. It is type 2 modification. For example, suppose this is the reference bus 1, 2, 3, and suppose this is the ith bus. This is I plus 1 and this is n. Now this is Q is the new incoming node, ZS is the new element connected between Q and the ith bus. Yes or no? Again the number of buses are going to be increasing by 1, so it becomes n plus 1, and the new bus, Z bus, you are writing as, write the Z bus old, add ith, add a new row here and a new column here. The diagonal element of this new row and new column is going to be ZII plus ZS, and copy the elements of ith column here and copy the element of ith row here. So it becomes ZI1, ZI2, ZIN. Is it clear? Type 2 modification. Write the old Z bus, add a new column, add a new row, diagonal element is Zii plus Zs. Copy the elements of ith column here, copy the elements of ith row here, and you will get the type 2 modification. Is it clear, everybody? Type 3 modification. When a new element is connected between the existing bus and the reference bus. Now the new element is connected, but no new node is connected. So the number of nodes are going to remain same. It is not changing. Suppose you are connecting the element Zs between the ith node, already existing node, and the reference bus. It is 1, 2, 3 up to n. Then how you are writing the Z bus new? Z bus new is going to be Z bus old minus 1 upon Zii plus Zs. Write the ith column here and the ith row here and multiply it. It is Zni. It is Zni. This is Zni. Okay, this is Zin. Are you getting this? At least tell me yes or no. Z bus new is Z bus old minus 1 upon Zii plus Zs, ith column multiplied by ith row. Type 4 modification, this is the last one. When a new element is added between the two existing buses in the system except the reference bus. Suppose a new element you are connecting is Zs between I and k, and this is 1 to n, the other buses. Then Z bus new is going to be Z bus old minus 1 upon Zii, Zkk plus 2Zs. I think it should be minus 2Zik. It should be minus 2Zik multiplied by. Now you have to write element by element. Ith column element minus kth column element. Take one element of the ith column, take one element of the kth column, subtract it and write it here. Take one element of the ith column, one element of the kth column, subtract it and write it here. This is the way how you have to write it. I hope you are getting this. Multiply it by a row matrix where each element you have to write as the ith row minus kth row element. Take one element from the ith row, take one element from the kth row, subtract it and write it here. I hope it is clear. It should be Zi1 because it is ith row, na? So row comes first. This is Zin and this is Kn. Everybody just tell me in the comment section if you are able to follow this, then okay. Otherwise, if you have any problem, you can ask me. So now we will be starting the load flow analysis. If you have any doubt, you can ask me. So we are done with the revision of network matrices now. Okay. Okay. Just give me one moment. Thank you. Thank you. Suppose I am assuming that you have not read load flow analysis till now and this is the first time you are reading load flow analysis. So my intention is going to be that this is the very first attempt in which you are going to understand completely what is load flow analysis. Suppose somebody give you a call, your old friend, and he or she is asking, how are you? So what you do? You generally take a selfie and send it to your friend, yes or no? Similarly, if I am going to ask you, how is your power system, then what you will do? You will take a selfie, a photo of the power system and you will send me. Hello? Are you able to follow this or not? If I ask you, how is your power system, what you will do? You will take a selfie and you will send it to me. Now, so just I am giving you this to make you understand. Don't say this in front of any interview or somewhere, otherwise people are going to laugh at you. Okay. So load flow analysis is basically the selfie of the power system. Selfie of the power system. Selfie of the power system means it is a photo. Photo means what? It is static. Because when somebody is taking your photo, what they are saying? Don't move, don't shake your legs, don't shake your hands. Why? Because it is stand still. Then your photo comes good. When it is static, when it is photo, when it is selfie, that is why we are saying load flow analysis is a steady state analysis. Steady state analysis. So you remember, load flow analysis is a steady state analysis. Clear? Now, as I told you, load flow analysis is like taking the selfie of the system, telling somebody how your power system is actually performing. So basically, there are 4 parameters which are important in your power system. Those parameters are P, Q, voltage magnitude and del. At any bus of your power system, if you have these 4 parameters, you can find any data, any information required for your power system if you have all these 4 datas with you. Are you getting this or not? Say yes or no. The problem is, in our system, in our power system, there are different types of buses. Some of the buses, some data is already given, some data you have to find. It means there are some known quantities, some unknown quantities. Finding the unknown quantity is nothing but load flow analysis. Now you will say, if it is so simple, just finding the unknown quantities at some buses, different buses, then why we are so much worried about load flow analysis? The reason is, my friend, these equations are not linear equations. Ax plus by plus c is equal to 0. It is not like that much easy. These are non-linear equations. Non-linear equations, and that too not 1 or 2. N number of non-linear equations you have to solve simultaneously, and that is the reason you need some mathematical tools to perform the load flow analysis. So something for your notes. Very fast you can write if you want. Load flow analysis is nothing but the solution of n or any number of non-linear equations to get the unknown quantities at certain buses. That is your load flow analysis. Is it clear, everybody? Are you able to follow this? See, you have to understand it like a story, otherwise you will, let me tell you, for most of the people, most of the electrical engineer, load flow analysis is a nightmare. Even though it is one of the most simple topic you can understand if you have the logic, if you have the story. I hope you are getting it. So before you perform the load flow analysis, you require some input data. What is this input data? Some of the buses, some quantities are known, some quantities are unknown. So the known quantities you require before you start the load flow. At the same time, you require Ybus also. Just now we have understood how to find the Ybus. Then you require methods to solve the non-linear equations, and finally you are getting the result, which is nothing but the information which you acquire after the successful completion of load flow analysis. If you talk about the types of buses in power system, so basically there are 2 types of buses in our power system: generator bus and load bus. Generator bus is bus on which at least one generator is connected. Generator bus is a bus on which at least one generator is connected, whereas a load bus is a bus on which no generator is connected. Yes or no? Now let us focus on generator buses. Generator buses can be of 3 types. Number 1, PV bus. It is the most simple generator bus. Why it is so named PV? Because P and V, these 2 quantities are known. These are specified quantities. That is why it is named as PV bus. What are the unknown quantities? You don't know del. You don't know the reactive power. That is why it is named as PV bus. It is the most simple bus in the power system. Then we have voltage controlled buses. Voltage controlled bus is a special type of generator bus which has some voltage control capability. I don't know what it is. It may be a reactive power compensation. It may be tap changing transformers. It may be some other method through which you can control the voltage of that particular bus, and this is a generator bus which has some voltage control capabilities. Now you have a slack bus. Slack bus, it may be one or more than one in a system. What is the purpose of slack bus? Let us understand. Suppose this is your system. Okay. So there are n number of buses, transmission lines, so many things are there. When you are writing the equations for all these buses and the transmission lines in the system, you don't know the losses. At the first place, you don't know the losses in the system because you have to calculate the losses. And the second point is, you don't know the losses first place. Second, you don't know how to allocate them. I don't know how much loss is here, how much loss is here, how much loss is here, how much loss is here. So I am doing something smart. What I am doing? I am aggregating the losses of the system and I am giving this responsibility of losses to one bus in the system that I am defining as the slack bus. Slack bus is going to supply all the losses in the system. It may be one, more than one also. So generally the largest generator bus in the system is taken as the slack bus. The concept of slack bus and reference bus is different. Slack bus is meant to supply the losses in the system at the end of the load flow, but the reference bus is used as a reference. But generally in most of the system, we are using the slack bus as the reference bus. So don't confuse with it. So if you define the slack bus, the total losses in the system remains unknown till the end of one or more, till the end. So till the end of load flow analysis. Till the end of load flow. Hence, one or more generator buses are assigned as slack bus, which is supposed to supply the total system losses. Generally, the largest generator bus in the system is taken as the slack bus. Slack bus may be more than one as per the requirement, but generally one bus is taken as the slack bus. It is also called as swing bus. It is also called as swing bus. Why it is called as swing bus? You know the children swinging? Because you don't know the losses. It may be here, it may be here, it may be here. It is swinging. The real and reactive power supplied are going to be changing. That is why it is also called as swing bus. The slack bus and the reference bus are different concepts, but generally for the simplicity, slack bus is chosen as the reference bus. Now in the load flow solution, okay, if you talk about the slack bus, for the slack bus, P and Q are unknown because this is what being supplied to the overall system as losses, P and Q. Voltage, magnitude and del is known. Specified quantities, generally we are assuming magnitude as 1 and generally we are assuming del as 0 for the slack bus. Yes. Now let us talk about PV bus. PV bus is a generator bus. The specified quantities means known quantities. So P is known, voltage, magnitude is known, Q is unknown and del is unknown. If you talk about the load bus, voltage controlled bus. Now voltage controlled bus is again a special type of generator bus which has some voltage control capabilities in it. For example, tap changing transformer, reactive power compensation, etc. So here P and V, like any PV bus, specified quantities, and Q and del are unknown or unspecified quantities. Now there is one glitch. What is that glitch? Suppose you are using shunt capacitors. Suppose you are using shunt capacitor compensation. So how much shunt capacitor compensation you are using? It means you must be knowing what is the reactive power status. Yes or no? If you want to help your friend wants some money and you are telling your friend, okay, I will give you some money. You have 1000 rupees in your account and your friend wants 10 lakh rupees. Can you help him? No. So before you help your friend, you must know what is the status, economic status of your friend, what is the demand. So if you want to compensate the reactive power, you must know what is the reactive power status at the bus. So if that voltage controlled bus has a shunt capacitor compensation, my friend, please remember, P is known, Q is known, voltage magnitude is known, the only unknown is del. And this is the reason, in that case, this type of bus, it is a PV bus, it is a generator bus, but it is taken as a PQ bus. It is treated as a PQ bus. I hope you are able to follow this. This is the reason. Then we have load bus. The name itself tells you PQ bus. PQ bus means P is known, Q is known, magnitude V is not known, del is not known. P and Q known. That is why it is named as PQ bus. Okay. So you can understand almost 85% of the buses in your system are going to be the load buses. Almost 85% of the buses are load buses. Around 5 to 10% buses are going to be the generator buses. Is it clear? So let us start the load flow analysis. Input data required, you require the Ybus. At the PV bus, you want P and V. At the voltage controlled bus, you require P, Q and V. And what is the information you are, and at the load bus, that is PQ bus, you know what is P, you know what is Q. Okay. And what is the information obtained? What is the solution of load flow analysis? PV bus, you are getting Q and del known, because Q was unknown, del was unknown, so you are finding Q and del. PQ bus, that is the load bus, you are finding voltage magnitude and del. Voltage control bus, you are finding del. Finally, you are finding the losses in the system by using the slack bus P and Q. Then you are finding line flows, real and reactive power. If you know the voltages, if you know the Ybus, very easily you can find the load flow, yes or no? Remember or not? What is P? V1, V2 upon X sin del. If you remember. Similarly, you can write for Q also. I hope it is clear. So if you know the voltages, if you know the Ybus, very easily you can find what are the real and reactive power flows in the various parts of the system. Is it clear, everybody? Are you getting some idea how we are going to proceed for the load flow analysis? Before we talk about different methods of load flow analysis, it is important that we talk about the static load flow equations. How you are writing the static load flow equations, this is very important. Let us take a random bus. Suppose it is the ith bus in your system. One generator is connected, some load is there. Generator is supplying real and reactive power PGI, QGI. The load is taking PDI and QDI. So the power which is injected at this bus, I am writing as PI plus JQI. So PI, I am defining as PGI minus PDI. QI, I am defining as QGI minus QDI. Is it clear, everybody? This is called injected real and reactive power at any bus. So whatever equations we are going to talk about, these equations are going to be about injected real and reactive power. I hope it is clear. So we are defining the injected real power as PI, PGI minus PDI. Injected reactive power QI as QGI minus QDI. Now how you are writing this injected power at any bus? You can write it as voltage multiplied by the complex conjugate of current. Yes or no? Take the complex conjugate both the sides, because we want to free the current. We want to write the current in this manner. So it will be complex conjugate of SI is equal to complex conjugate of VI multiplied by II. This becomes PI minus JQI. it becomes Pi minus JQi. Is it clear, everybody? Are you able to follow this or not? Then I'm writing the current. Now see, writing current is very easy, interesting. It is like you are writing the KCL, Kirchhoff's current law. It is going to be summation. It is Yik Vk, and K is going to vary from 1 to n. I is fixed. Whatever bus you are talking about, I is fixed. K you have to vary from 1 to n, Yik Vk. This is how you are writing. So it is Yik Vk and K is going from 1 to n. Just put this value of current in this equation. So you will be getting Pi minus JQi, Vi complex conjugate, this. From here, you take this Vi complex conjugate inside and separate the real and imaginary part. Okay, so it is not mentioned here, so let me write it here. Let me add some pages here. Just see how you are writing. You are writing Si complex conjugate as Pi minus JQi. This is summation K 1 to n. This is Vi complex conjugate. This is Vk and this is Yik. Now let us assume Vi is magnitude Vi angle del I. Assume Vk is magnitude Vk angle del K. Assume Yik is magnitude Yik angle theta Ik. So you can write it all these values here. So it becomes summation K 1 to n. It becomes mod Vi, mod Vk, mod Yik, and the angle. Now I'm writing the angle here. So it becomes del K plus theta Ik minus del I. Just separate the real and imaginary part, you will get the Pi and Qi equation. What is Pi? Separate the real part. So it becomes magnitude K 1 to n mod Vi, mod Vk, mod Yik. This is cos of theta Ik del K minus del I. When you write the reactive power injected Qi, you have to take care of one negative sign because it is minus, na? So it is minus K 1 to n mod Vi, mod Vk, mod Yik. This is sine of theta Ik plus del K minus del I. I hope you are getting this. It is so easy. I don't know why students fear from it. Yes or no? Just tell me yes or no. Are you able to write these equations? And these equations are nothing but V1, V2 upon X sin del or cos del. This is just the general way of writing it. Now to solve the non-linear equations. These are non-linear equations, yes or no? These are non-linear equations. These are P and Q are non-linear equations. To solve these non-linear equations, you require some mathematical tools. That mathematical tools we are using. And on the basis of that, you are getting different methods. The first one is Gauss method. Then we have Gauss-Seidel method. Then we have Newton-Raphson method. Then we have decoupled load flow. Then we have fast decoupled load flow. Okay. So I want all of you to now focus. Important things going to come. If you talk about the Gauss method, the idea is to represent x as a function of x only. If you are doing it through the Gauss method, the idea is to write x as a function of x only. For example, you have the equation tan x minus 1.5x. Just put it to 0. Okay. So you can write x as tan x upon 1.5. Sorry, it is x you are writing as tan x upon 1.5. Everybody is getting that? X is tan x upon 1.5. For Gauss method application, you have to write x as a function of x only. Now keep on putting different values for x and get the new value. See the difference. If that difference is less than a certain value, your solution is converged, you got the solution. If not, keep on putting the values, new values, different iterations. For example, you are assuming the initial guess. Now in power system, it is very easy to make the initial guess. Because yesterday night what was the load, that is going to be the same morning also. It is not that overnight somebody has built the industry. Are you getting this? So giving you a guess in the power system is very easy. Overnight loads and power flow is not going to change drastically. You have a good amount of initial guess in the power system. Now x is equal to x naught is the initial guess. Just put this value here. So what you are getting? You are getting x1 as tan x naught divided by 1.5. This was the equation. What you are getting as x1 becomes the input for the second iteration. Second iteration x2, it is going to be tan x1 upon 1.5. Similarly, for r plus 1th iteration, if you write it for r plus 1th time, it is going to be tan xr divided by 1.5. Now you have to check the difference between xr plus 1 minus xr. In any two iterations difference you have to see. If it is less than a predetermined value epsilon, which is the acceptable limit, acceptable error. It is a positive value, small positive value. If it is less than a predetermined value, this difference, then you stop, the solution is converged. Now I'm going to tell you some funny thing. Gauss method is like you want to go somewhere. From your home, you want to go to the railway station. So what you have done? There is a blindfold on your eyes. You don't know where to go. There is nothing, no help. And simply you are coming out of your home and you are searching where is the railway station, where is the railway station. Every moment you are getting a collision. You are colliding with somebody, some people, you are asking, where is the railway station? He is saying that side, 2 kilometers right, take a sharp turn. Gauss method is like this only. So there is a possibility the number of iterations are going to be very large for Gauss method. But the time for one iteration is very less. The moment you collide with somebody, sir, where is railway station? Madam, where is railway station? So time per iteration is very less, but the number of iterations are going to be very large. And there is a possibility that the initial guess, if the initial guess is wrong, then there is a high possibility that even your solution may not converge with the help of Gauss method. I hope you are getting it. Everybody is getting that? Gauss method. How you are doing this Gauss method in the power system? Again, you are writing the current like this. Sigma K1 to N Yik Vk. Now I am separating the K is equal to I term. K is equal to I term, I am separating. So II becomes Yii Vi because K is equal to I, separating, plus sigma K 1 to N K not equal to I Yik Vk. This is how we are writing the current. You must understand. Why I am writing like this? Because I have to write X in terms of X. This is the basic requirement of Gauss equation, Gauss method. Just put it here. The complex power you are writing as Vi complex conjugate. I value you are writing like this. Pi minus JQi. Just separate Vi. You are getting Vi as a function of Vi. 1 upon Yii. You have to remember this equation. All of you. This equation you have to remember. Vi is equal to 1 upon Yii, Pi minus JQi upon Vi complex conjugate minus sigma 1 to n k not equal to I. Yik Vk. I am just writing here again. Okay. Just see here. You are getting Vi as one upon Yii Pi minus JQi Vi complex conjugate minus sigma k1 to n k not equal to I Yik Vk. This is your equation which you are using for the Gauss method. You can remember this equation, it is important. It's not that difficult. 2-3 times if you practice, you can write it. Anybody can write it. Practice 3-4 questions, you will remember it. Okay. So finally you have got the equation for your power system, how to do it. Vi in terms of Vi, x in terms of x. How to do it in power system? For the r plus 1th iteration, how you are writing Vi r plus 1? It is 1 upon Yii, it is Pi minus JQi Vi r complex conjugate, because the rth iteration value you have to write as input. You remember? x1 is tan x naught upon 1.5. x2 is tan x1 upon 1.5. So Vi r plus 1 is Vi r complex conjugate minus sigma 1 to n k not equal to I Yik Vk r, rth iteration value. Now let us see case 1. When only PQ buses are present. This is the Gauss method. When only PQ buses are present. Only load buses are present. When only load buses are present, okay, out of the total buses, one bus is taken as the slack bus and rest of the buses are PQ bus, suppose. So if it is a PQ bus, you tell me, if it is a PQ bus, it means what? You know what is P, you know what is Q. What you don't know? Voltage magnitude and del. So for any bus, you have to write this equation of Vi. If you have this equation of Vi, you have the magnitude and phase angle, yes or no? So the step number 1 is construct Ybus. The first thing you should have is the Ybus. You have to construct the Ybus. Okay. Once you have the Ybus, now you get the injected real and reactive powers. Pi as Pgi minus Pdi. Qi as Qgi minus Qdi. For I 2 to n, because I is equal to 1 is the slack bus. Assume the initial guess and set the iteration count r is equal to 0 and take the tolerant limit for error as epsilon, some small positive value. Now you write the equation for the r plus 1th iteration, calculate Vi at each of the bus. So you will be getting magnitude and phase angle of the bus voltage, all the buses. Just write it. Okay. Now at every iteration, you check the error. VIR plus 1 minus VIR. The moment you get it less than epsilon, that is the permissible error, solution is converged, and go to step number 4. What is step number 4? Calculate the power injected by the slack bus and calculate the losses and line flows. If not, then increase the iteration count by 1, R as R plus 1, and go to step number 2. Again calculate the VI and check the error. Ashok is asking, sir, what is PDI? I hope you did not see when we discussed the injected bus powers. At any ith bus, if a generator is connected, PGI and QGI are the real and reactive powers generated, and PDI and QDI are the real and reactive power demand. So what is generated and what is supplied to the demand, after which what is remaining, is given to the system. It is injected to the system. That is why it is called as injected real and reactive power. Is it clear, everybody? I hope you are getting this. Everybody is comfortable with the Gauss method? Everybody is comfortable with the Gauss method? So let us solve this question. This question, let me add some pages. We are going to solve. He is asking find the voltage at bus number 3 at the end of the second iteration by Gauss method. 2 and 3 are the load buses. Okay, so this is the bus data. Bus number 1 we are choosing as the slack bus. Voltage magnitude del we have assumed 1 and 0. PG, PD, this is unknown because the slack bus ultimately has to supply the losses at the end of the load flow. Bus number 2 and bus number 3, these are the load buses. The generated power and the demand is mentioned here. Okay. Ybus is also mentioned. Okay. You have to find the voltage at bus number 3 after the second iteration. The first thing you have to find, the injected real power and reactive power for bus number 2 and 3. Listen very carefully. PGI for bus number 2, PGI minus PDI. So 0.8 minus 1, it becomes minus 0.2. QGI, reactive power, 1 minus 1, so it is 0. Bus number 3, PGI minus QDI, so 0 minus 1 is minus 1. Reactive power, 0 minus 0.8, so it becomes minus 0.8. So these are the injected real and reactive power you are getting at different buses, bus number 2 and bus number 3. Now I want to write the equation. What was the equation? You remember? The equation was VI R plus 1 is equal to 1 upon YII PI minus JQI upon VI, okay, R, Rth iteration value, complex conjugate minus summation K 1 to N K not equal to I YIK VK. This is the equation you have. Suppose I am writing for bus number 2. For bus number 2, I am writing the first iteration. See very carefully. Bus number 2, I am writing the first iteration. What is Y22? What is Y22? Y22 is minus J15. It is minus J15. Okay. Then PI for the second bus. For the second bus, it is minus 0.2 and QI 0. So minus 0.2 divided by VI. So it becomes V2. Initial guess you have to write and take the complex conjugate. Minus, listen very carefully. You have fixed the I. I has become 2 now. I has become 2 now. For all the rest of the buses, you have to range K1 to N. So it becomes Y21 V1. And this is also Rth iteration value you have to put. So initial guess I am putting minus Y23 V3 0. So this is going to be your first iteration value for bus number 2. The voltage for bus number 2 first iteration value. Everybody is comfortable writing this? You can get Y21, Y23 from the Ybus. You can get the initial guess also, or you can take some initial guess. Similarly, you can write for bus number 3 first iteration. For bus number 3 first iteration, you can write 1 upon Y33. What is Y33? Minus J5. Minus J5. Pi minus JQi. Pi minus JQi. So it is -1 minus plus J 0.8. It is V3 0 complex conjugate minus, it becomes Y31 V1 0 minus Y32 V2 0. Similarly, you can do the second iteration. For bus number 2 and bus number 3, put the values, you will get the answer. I hope you are getting this idea clear in your mind. Everybody just tell me yes or no in the comment section. Are you able to follow this or not? Is it clear, everybody? So this was the Gauss method. Now we are going to talk about the Gauss-Seidel. Gauss method, I told you, is like you are coming out of your home and you want to go to railway station and there is a blindfold on your eyes, and whenever you are hitting a person, you are asking, where is railway station? Where is railway station? Now Gauss-Seidel is going to do some modification. What Gauss-Seidel has done? Gauss-Seidel has actually given a stick in your hand. Still there is a blindfold on your eyes and there is a stick in your hand. Now you can go to the railway station little faster. Number of iterations are going to be less. Time per iteration is as usual less. The number of iterations are going to be reduced by some modifications. What are the modifications? The modifications are wait. Okay, before we talk about the Gauss-Seidel, okay, wait, there was a confusion because of the heading. Because of the heading, there was a confusion. Still we are in the Gauss method because one case is solved, one case is not solved. We have solved the case when only PQ buses are present. When both PQ and PV buses are present, then how to do it? Are you getting this? So we'll do it again. Okay, we'll do it again after completing this. Then we'll talk about Gauss-Seidel. Let us take the second case when the PV buses are also present with the PQ bus. Not only PQ buses are present, PV buses are also present. When PV buses are also present, listen very carefully. Suppose one bus is defined as a slack bus. Now bus number 2 to bus number M, you have PV buses, and M plus 1 to N, you have PQ buses. Are you getting this? One bus slack bus, bus number 2 to M PV buses, and M plus 1 to N PQ buses. Step number 1, construct Ybus and then calculate the injected real power and injected real power and reactive power. This is step number 1. Step number 1. Assume the initial guess. Take the magnitude of voltages as 1. Okay. And take del I angle as 0. Now voltage magnitude you are going to choose only for the PQ buses. That is why it is M plus 1 to N. Only for PQ buses. Whereas the del angle you want both for PV buses and PQ buses, because del is unknown for PV bus also and PQ bus also. Is it clear, everybody? Say yes or no. Set the iteration count 0. Take the tolerance epsilon. Now, before you start the load flow solution, all the PV buses you have to find QI. Why you are finding QI? You know the equation, steady state power flow equations we have just read. Because you have to know the Q value for all the PV buses, because that is unknown for all the PV buses. So first you have to find it by using this equation. It is del I minus del K. This is del K. Okay. So you are first finding Q for all the PV buses because Q is unknown there. Are you getting that? Then you are writing the voltage equation like you have written it for the previous method. It will give you the voltage magnitude also, and it will give you the phase angle also. I hope you are getting this. The basic idea you please understand. A lot of confusion is going to be there. I understand. For PQ bus, for every iteration you have to find the voltage magnitude and the phase angle. This is the case. For PV bus, at every iteration you have to find the Q value and del value, because P is known, V is known. So every iteration, every step you have to find Q. By using the V equation, you can find the angle of V as del. I hope you are getting that. This is how you have to proceed. Update del I at all the PV buses. Update VI and del I at the PQ buses. Unknowns you have to update because for the next iteration, they are going to act as the input. Now calculate Q at each of the buses, PV buses, because you got the updated values. Now listen very carefully. At this step number 5, number of times questions have been asked from this step. If you are getting this Qi less than Q minimum or Qi more than Q max, whatever limit is breached, you are going to fix it at that limit. If it is less than Q minimum, fix it at Q minimum. If it is more than Q max, fix it at Q max, like this. And for that particular iteration, that bus, that PV bus, you have to treat at PQ bus. For that iteration only. For that iteration only. For that iteration only. Okay. So check for the Q limits. Q greater than Q max, Qi is Q max, Q less than Q minimum, Q is equal to Q minimum. For that iteration, use the concerned bus as PQ bus, not the PV bus. And in the next iteration, again treat it as the PV bus only. Now again calculate the error. If the error is less than the permissible error, then go to step number 7, load flow converges, find the slack bus power, line flows. If not, increase the count, iteration count by 1 and go to step number 3, again do the calculations. Is it clear, everybody? I hope you are getting some idea. Not 100% maybe, but at least some idea, some clarity you must be getting. And that is very important. Because one more reading you require to completely get confidence over this. Self-study. Now let us talk about the Gauss serial. As I told you that Gauss was like no help, blindfold on your eyes going from your home to the railway station, and Gauss serial is like, yes, I will provide you the telegram. Yeah, I will provide you the PDF in the telegram, don't worry. Okay. Gauss serial is like, Gauss serial has given a stick in your hand. There is a blindfold on your eyes, there is a stick in your hand. So your number of iteration becomes less. You are reaching to the railway station faster. How? Because of two modifications. Number one, in any iteration, use the latest available values. What was the mistake done by Gauss? Listen very carefully. When you are writing R plus 1th iteration for the ith bus, listen very carefully. It's okay. When you are writing the R plus 1th iteration for the ith bus, it means already you have written R plus 1th iteration for I minus 1th bus. Hello. Before I, already you have got the R plus 1 updated values. Then when you are writing this equation, why not you are using the R plus 1th iteration value? Why still you are using the Rth iteration value? It is going to slow down your solution convergence. That is the reason we are writing a new equation with the updated values. Vi R plus 1. 1 upon Yii, Pi minus Jqi ViR, complex conjugate, minus K1 to I minus 1. I hope you are getting this. K1 to I minus 1 We are writing yik vk r plus 1. R plus 1th iteration updated values you have to put here. Before I, up to 1 to I minus 1, you have to put the r plus 1th values. Now I plus 1 to nth, you have to put the rth iteration value. I hope you are getting this. So use the updated values. This is the first modification. Second is use the acceleration factor. This is going to increase your speed to get the solution. Acceleration factor is defined as VIR plus 1 accelerated value is going to be the input for the next iteration as VIR plus alpha, VIR plus 1 minus VIR, where alpha is the acceleration factor. Its value varies from 1.2 to 1.6 or 1.8, whatever. And this is the accelerated value. Apart from these two modifications, rest everything is same in Gauss and Gauss-Seidel. Is it clear, everybody? Is it clear? Now let us talk about one of the most popular, one of the most famous one, that is the Newton-Raphson method. Just give me a moment. So let us talk about the Newton-Raphson method. Everybody is okay till now? Any doubt you can ask me. Everybody is okay with that? Now Newton-Raphson is like a revolution. The blindfold from your eyes is removed and it has given a GPS in your hand. You don't need to ask anybody. Set the location, destination, and within no time, and it is going to book a cab also for you. Newton-Raphson method. Because irrespective of the size of the system and the initial guess, whatever network you are going to get, irrespective of the size of the system or the initial guess, the solution is going to be converged within 3 to 4 iteration. Within 3 to 4 iteration. That is the power of Newton-Raphson method. It is so because it has a quadratic convergence. Very fast it is going to converge. Very fast. Now, there are no free lunches in life. If you get something from one hand, then you have to give something from the other hand. It's all about give and take. If you are getting the solution within 3 to 4 iterations, it means the time per iteration is going to be large. So the time per iteration is large. Why the time per iteration is large? Because every iteration you have to calculate the inverse of the Jacobian matrix. You have to find the inverse of the Jacobian matrix in each iteration, and hence the memory requirement is very large. You will say, sir, why? What is the problem? The problem is, if I ask you to find the inverse of a 2 cross 2 matrix, you will say, whoa, sir, maza aa gaya, maza aa gaya. But if I increase the system size by 1, if I say, find the 3 cross 3 matrix inverse, you will give that work to your calculator, scientific calculator. Now, if I increase the number of system, size of the system, number of buses in the system by 1 more, 4 cross 4 matrix, ask you to find the inverse, then your calculator is going to raise hands. Sorry, brother, can't do it. We are talking about a system, hundreds of buses may be there in the system. Can you imagine the kind of memory requirement to process that particular inverse matrix? Yes or no? Inverse of the Jacobian matrix you have to find in each iteration. That is why the time per iteration is going to be very large. How you are doing this Newton-Raphson method, let us understand very carefully. You represent the non-linear equation as fx is equal to 0. Represents the given nonlinear equation as fx is equal to 0 and let x naught is the initial guess, x naught is the initial guess, and let delta x is the change or error in the initial guess. So just add the error in the initial guess, you will get the final answer. So I am writing f of x naught plus delta x as 0. Now expand it as per the Taylor series and ignore the higher order terms. So you will be getting the Taylor series expansion as fx naught plus delta x upon factorial 1 f dash x naught plus delta x square upon factorial 2 f double dash fx naught plus dot 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 equal to 0. Now this f dash is the differential, first order differential, f double dash is the second order differential, and this is how you are going to proceed for the Taylor series. Now higher order terms you are going to neglect. So you are only focusing on these two terms. These terms you are going to neglect as 0. So it becomes fx naught plus delta x f dash x naught, because factorial 1 is 1, is equal to 0. How you can write the error? You can write the error delta x as, minus of fx naught divided by f dash x naught. So you got the expression for error. This is what you have to follow in the Newton-Raphson method. If you know the function, if you know the initial guess or input value, you can find the error. Now after some iterations, the solution is going to be converged when the error is going to be less than the permissible error. Now first iteration, how you are writing first iteration? x1 is going to be x naught plus error. What is plus error? Minus fx naught upon f dash x naught. Second iteration, what is x2? x2 is, it is x1 now. x2 is x1 plus delta x1. What is delta x1? fx1 upon f dash fx1. I hope you are getting this. So r plus 1th iteration, xr plus 1th iteration is xr plus delta x r plus 1. What is delta x? It is minus of fxr upon f dash xr. So this is how you are finding the error in case of Newton-Raphson method. Now you have n number of nonlinear equations. Suppose f1, which is a function of x1, x2 up to xn, is equal to y1. Similarly, f2 as a function of x1, x2, xn up to xn, and y2 is equal to y2. fn, x1, x2, xn, yn. Now this y1, y2, yn, these are the specified values already mentioned. You know these values. So you are going to write these with the initial guess. If you write the initial guess, so you are going to put x1 as x1 naught, x2 as x2 naught, xn as xn naught. So you are getting x as x1 naught plus delta x1, x2 naught plus delta x2, like this, and you do the Taylor series expansion like you have done before. Initially we were talking about only one equation. Now there are n simultaneous nonlinear equations we are solving. So for one equation, if you write, listen very carefully, I am writing for I am not writing for higher order terms, only for the first two terms I am writing. So it is going to be f1 x1 naught, x2 naught up to xn naught plus, what was the error? What was the error? Delta x upon factorial 1 del f1 upon del x1. This is delta x1 because f is a function of x1, x2 up to xn. So for all the variables error you have to add plus delta x2 upon factorial 1 del f1 upon del x2. Similarly you write for all of them is equal to y1. y1 is the specified value. What is this? f1 x naught, it is the calculated value. This calculated value I will take to the right hand side. So this equation you will be getting as, see here, first equation I am writing differentiation multiplied by delta x1, differentiation multiplied by delta x2 up to this is equal to y1 minus f1 x naught. This is the specified value. This is the calculated value. Specified value means which was already known in the question. Calculated value means you have put the initial guess and then you have found it. The difference you can write like this. So for every function, this was for f1, this was for f2, this is for fn, you are writing it. Now this system of equation you can write in matrix form. This you can write as, what is this delta f1, delta f2, delta fn? It is the specified minus calculated value. Specified minus calculated value I am writing as delta f1, something like this. So now if you write in terms of matrices, it becomes the differential matrix, which is called as Jacobian matrix, and the error matrix, delta x1, delta x2 up to delta xn. If you have this relation, can you write the error matrix? Yes. This Jacobian matrix you have to take here. So you have to take the inverse of the Jacobian matrix, and this is delta f. And this is the reason I am telling that every iteration you have to find the inverse of the Jacobian matrix. Every iteration you have to find the inverse of the Jacobian matrix. Is it clear, everybody? Is it clear, everybody? Tell me yes or no. I hope you are able to follow this. Waiting for your response. When you apply this to the power system, okay, let us come to the Newton-Raphson. When you apply it to the power system, you get equation like this. This is delta P, delta Q. This is the Jacobian matrix. This is the Jacobian matrix. H, N, M, L. These are the submatrices. These are the submatrices. H itself is a matrix. N itself is a matrix. M itself is a matrix. L itself is a matrix. And this is the error matrix, delta del and delta mod V. Now H, listen very carefully. H represents the variation of P with respect to del. So it represents del P upon del del. N represents the variation of P with respect to V. So it becomes del P upon del V. Similarly, M submatrix represents the variation of Q with respect to del. L matrix represents the variation of Q with respect to del V. I hope it is clear for all of you. Is it clear? Now, one of the most famous question which was asked in this concept is, this is L, this is M, this is L, this is M. So somebody asks you the size of the Jacobian matrix. Okay, size of the Jacobian matrix. So if this is L, this is M. So number of rows L plus M, number of columns L plus M. So what is the size of Jacobian matrix? It is L plus M cross L plus M. What is L and M? L we are defining as number of P specified. Now P is specified on PQ bus also, and P is specified on PV bus also. So number of PQ buses plus number of PV buses will give you L. What is M? Number of Q is specified. Q is going to be specified only on the PQ bus. So number of PQ buses is going to be equal to M. That is the number of Q is specified. Are you getting this? So not only the Jacobian matrix size, you can get the size of all the submatrices also, if you know the L and M values. Yes or no? For example, H matrix, number of rows is L, number of column M. So H is L cross L. H is L cross L. Matrix N, number of rows L, number of column M, L into M. So it is L into M. M submatrix, number of rows M, number of column L, M into L. It is M into L. L submatrix, number of rows M, number of column M. So M into M, the L submatrix. Is it clear, everybody? I hope it is clear. Now let us do one question. He is saying a power system network comprises 100 buses. So the total buses in the system is 100. Out of which there are 10 generator buses. There are 10 generator buses. 5 buses are reactive power adjustment buses. 5 buses are reactive power adjustment buses and the other buses are load buses. So out of 100 buses, if you remove these 15 buses, they are going to be PQ bus. So it is 100 minus 10 plus 5. So it becomes 85. What is the number of PV buses? Number of PV buses, listen. Total how many generator buses? 10 plus 5. One of the bus you have to take as slack bus. So 15 minus 1 is going to be total number of PV buses. Yes or no? Can you tell me what is L? Can you tell me what is L? L we are defining as number of P specified. P is specified PQ bus also and PV bus also. So 85 plus 14. 85 plus 14. 5 4 9, 8 1 9. What is M? Number of Q is specified. Q is specified only on the PQ bus. So it is 85. What is L plus M? 9 5 14 के 4 हासिल लगे 1 8 1 9 9 18 184. So what is the size of the Jacobian matrix? It is 184 into 184. Is it clear, everybody? So my energy may be showing a little bit dip. I think I am getting a fever, but it's okay. We will continue the session because we have to finish the remaining portion. Very small portion is remaining. Okay. Anyways. Now, what we are doing? We are doing some modifications. Okay. What? This equation delta P delta Q H N M L delta del delta V, we are doing some modification. What is that modification? We are dividing this by magnitude V, this change in the voltage magnitude. Ashok is saying that I am not getting, try again. Okay, you tell me exactly where you are not getting. Ashok, you can ask me. Listen very carefully. Once you apply the Newton-Raphson method in the, it's okay, Ram. Power system, finally you are getting this equation similar to what we have done earlier. Now this matrix, J matrix, we are defining as the Jacobian matrix. Its size is L, M, L, M. Okay, number of rows, number of columns are that. Now L and M we are defining as number of P specified and number of Q specified. I told you, when I say number of P specified, now P is specified means P is known. Where P is known? P is known on PQ bus, P is known on PV bus. So the number of PQ bus plus PV bus will give you L. What is M? Number of Q specified. Q is known on PQ bus. So the number of PQ bus is going to give you M. Now L plus M cross L plus M is the size of Jacobian matrix. Yes or no? Yes or no? What is the size of Jacobian matrix? Number of rows. L rows, M rows. Total how many rows? L plus M. Number of columns. L column plus M column. Total L plus M columns. So number of rows multiplied by number of columns gives you the size of Jacobian matrix. Is it clear, everybody? Ashok, I hope now you are getting. Listen very carefully. Now why I am dividing it by mod V? If I am dividing it by mod V, please understand. Please understand. When you are multiplying these two matrices, so H has to be multiplied to delta del, N has to multiply to delta V, M has to multiply to delta del, and L has to multiply to delta V. It means if you are dividing this delta V by magnitude V, then you have to multiply here also. This N you have to write as N into magnitude V. Then only the equation remains same. It becomes L multiplied by magnitude V. Then it will be cancelled. Yes or no? This is why we are writing here. So this becomes N dash and this becomes L dash. Why we are doing this? We are doing this. Okay, we are doing this because after this modification, the matrices that you are getting as n dash and L dash, their computation becomes easy. It is not that complex. It is similar. How? We'll understand. Now the most important part here is how to find these submatrices H, N dash, M and L dash. I will tell you few of them. Rest you can try at your home, because it is not possible to tell you each and every statement like that, because you have to understand it and apply it yourself. Now listen very carefully. We are writing the real power injected and reactive power injected like this. How? Listen very carefully. We have separated the K is equal to I term. You remember the equation or not? The equation was, let me write it here. For Pi, what was the equation if you remember? It was it was K 1 to N. It was mod Vi, mod Vk, mod Yik, and it was cos of theta ik plus del k minus del I, if you remember. This was the equation. Now K is equal to I, we have separated. So K is equal to I means Vi into Vi, because Vk becomes Vi, so Vi is square. So Vi is square. Now Yik cos del k del I same, when K is equal to I, it is cancelled. So it is Yik cos theta ik or theta II. Now what is Yik cos theta II? It is nothing but the real part of Yi. So it becomes Gii, that is nothing but the conductance. Similarly, when you are writing for the reactive power, it becomes Vi square Bii and plus the next part. I hope now you can correlate. So these equations you are going to use to finally write the values for H, N dash, M and L dash submatrices. For example, for H matrix, if you have to write, listen very carefully, you have to write Hik. What is Hik? Listen very carefully, you will understand it. You have to differentiate the P equation with respect to del K. You have to differentiate the P equation with respect to del K. Go to the P equation. This is your P equation. Differentiate it with respect to del K. This term becomes 0 because there is no del K term. Yes or no? Now when you are differentiating with respect to K, listen very carefully, this K can be 1 also, K can be 2 also, K can be N also, but K cannot be I. So you have to put the summation here. Are you getting this? Yes or no? Suppose you are differentiating it like this, del Pi upon del K. It means K you have fixed. Yes or no? For that particular differentiation, for that particular term, you have fixed the K. K may be 1, K may be 2, K may be 3, any value other than I. Now if you differentiate it, this summation will go. Yes or no? If you are differentiating with respect to del 1, suppose. So rest terms are del 2, del 3 up to this. So all that will be 0 because you have to differentiate only with respect to del 1. Yes or no? So what you are getting? Vi, Vk, Yik sine. Why sine? Because here it is cos. So what is the differentiation of cos? Minus of sine theta. So cos theta is minus of sine theta. So minus of sine theta ik del k minus del I. I hope you are getting this. Do you understand this or not? So these equations I am leaving on you. Okay, please cross check with them. If you are not getting it, then you can leave this also because it will take some of your time, crucial time. So I am not saying that you do it 100%. Whatever till now we have discussed, that will be sufficient for your GATE examination. And I can give you one simple thing also, simple way of doing this also. If you are not comfortable with these equations, no problem. Can you write these equations? Can you write this equation? V1, V2 upon X sine del. Can you write this equation? V1, V2 upon X cos del minus V2 square upon X. Can you write this? Just simply del P upon del del. Yes or no? Del Q upon del del, del P upon del V1. So these are nothing but these equations only, P and Q. The general way of writing it is like this only. So for numerical questions, you can follow it. You can do the simple way. So this was the Newton-Raphson. These calculations you can cross-check. Now coming to the decoupled load flow. What is this decoupled in decoupled load flow? If you see, P is sensitive towards changes in del, but P is not sensitive towards changes in magnitude V. Similarly, Q is sensitive towards changes in magnitude V, but Q is insensitive towards changes in del. So what I'm going to do is, I'm going to write on the basis of this decoupling that del P upon del magnitude V, we are assuming it to be 0. Similarly, del Q upon del del, I'm assuming to be 0. So what happens? Your matrices becomes simple. Out of this H, N dash, M, L dash, this N dash and M dash becomes 0. So your final equation becomes like this only. But still, in every iteration, you have to find the Jacobian matrix. So the time per iteration is going to be quite large, but it is little faster than the Newton-Raphson method. I hope you are getting this. So Jacobian matrix non-zero elements are heavily reduced. Memory requirement is less, but still the inverse of Jacobian matrix has to be found in every iteration. So time per iteration is going to be significant. Now coming to the fast decoupled load flow. Fast decoupled load flow, I am not going to tell you much because a lot of approximations we have to do. I am just going to tell you the shortcut way of doing it. The theory part you can see. You have to simply write the B dash and B double dash matrices. If you are able to write B dash and B double dash matrices, you can write the Jacobian matrix. And the beauty of this fast decoupled load flow method is that the Jacobian matrix is assumed to be a constant matrix, so that its inverse has to be found only at the starting of the load flow, not in every iteration. This is the beauty, and it is going to save lot. It is going to save lot of your time. It is going to save lot of your time. Are you getting this? And this Jacobian matrix you can find by using B dash and B double dash. What is B dash and B double dash? B dash is simply, it is the imaginary part of Ybus matrix when the slack bus row and columns are removed. Remove the slack bus row and columns from the Ybus and take the imaginary part only. That will become your B dash matrix. What is B double dash matrix? It is the imaginary part when both the slack bus and the PV buses row and columns are removed, and you take only the imaginary part. That will make your B dash matrix. Okay. So this is all about today's session. I hope you enjoyed the session, completing the load flow analysis. Okay. So this is about the GATE and ESE test series, which you can follow on BYJU'S Exam Prep app. You will be getting full length mocks, unlimited access to full length mocks, subject test. The link is given in the description. Some of the important features of these test series is 60 plus tests covering GATE and ESE, detailed mock analysis, virtual scientific calculator, 4,000 plus practice questions, all India open mocks curated by GATE experts. So this is all from my side, friends. Thank you so much for joining me live in the discussion. I hope you enjoyed the session. You learned a lot. So if you have any more confusion, any more doubt related to the load flow analysis, I will give you some questions in the Telegram channel. Okay, right now I don't have the questions. You solve them and you discuss with them. So I'm just giving you my personal Telegram channel on BYJU'S Exam Prep. That is Electrical by Ashutosh Sir. Electrical by Ashutosh Sir. So you can just hit the like button, hit the bell icon and subscribe to BYJU'S Exam Prep if you have not subscribed till now. Thank you so much everybody. Take care. Thank you. Thank you.